Welcome to Math Tutorials. In this video, we are solving every question of the miscellaneous exercise on Chapter 5, Continuity and Differentiability, from the NCERT Mathematics textbook for Class 12, Part 1. The miscellaneous exercise on Chapter 5 has 22 questions sweeping the whole chapter. Chain rule and logarithmic differentiations, parametric and implicit problems, second-order identities, and 3 beautiful theory questions. Here is the full list. Question 1. A quadratic raised to the 9th power, a straight chain rule. Bring the 9 down, drop the power by 1, multiply by the inner derivative. Chain rule with the inner derivative 6x minus 9. Factor 3 out of the bracket. Question 2. A cube of sine plus a 6th power of cosine. Each term is a power of a trig function. 2 chain rules. Power rule, then inner derivative on each term. Factor 3 sine x cosine x. Question 3. A variable base with a trigonometric exponent. Logarithmic differentiation. Logs bring the 3 cosine 2x down as a factor. Take logs. Product rule, minus 6 sine 2x times the log, plus 3 cosine 2x over x. Multiply back by y. Question 4. Inverse sine of x root x, which is x to the 3 halves. Rewrite the inside as a power before differentiating. The inside is x to the 3 halves, so its derivative is 3 halves root x. Divide by the root of 1 minus the inside squared, which is 1 minus x cubed. Question 5. An inverse cosine over a square root. Quotient rule with 2 chain rules inside. Compute the 2 derivatives first, then assemble. The numerator differentiates to minus 1 over root 4 minus x squared. The denominator to 1 over root 2x plus 7. Quotient rule, then split into 2 clean fractions. Question 6. A fearsome inverse cotangent of a ratio of square roots of 1 plus and minus sine x. Half-angle squares hide inside both roots. The whole tower collapses to x over 2. Write 1 plus and minus sine x as perfect squares of cosine half x plus and minus sine half x. On this interval, both brackets are positive, so the roots drop. The ratio becomes 2 cosine half over 2 sine half, cotangent of half x. Inverse cotangent of cotangent gives half x, whose derivative is 1 half. Question 7. Log x raised to log x, logs on logs. One more logarithm untangles it. Take logs. Log y is log x times log x. Product rule, both terms produce a factor of 1 over x. Multiply back by y. Question 8. Cosine of a linear combination of cosine and sine. A single chain rule, the constants ride along. Minus sine of the inside times the inside's derivative. Tidy the signs. Question 9. A function raised to itself, sine minus cosine in both base and exponent. On the given interval, the base is positive, so logs are safe. Let u be sine minus cosine, so y is u to the u and log y is u log u. Note u prime is cosine plus sine. Differentiate. U prime log u plus u prime, factored as u prime times 1 plus log u. Multiply back by y and restore u. Question 10. 4 powers, one of each kind. Variable to variable, variable to constant, constant to variable, constant to constant. Each type has its own rule. The last term is a constant and vanishes. X to the x gives the log formula, x to the a the power rule, a to the x the log a factor, and a to the a nothing. Question 11. Two variable-to-variable powers that swap the roles of base and exponent. Logs on each term separately. First term, log u is x squared minus 3 times log x. The product rule gives 2x log x plus the fraction. Second term, log v is x squared log of x minus 3. Add the two results. Question 12. A parametric pair shaped like the cycloid from exercise 5.6. Half angles will compress the ratio again. Differentiate both with respect to t. Half angle identities. The ratio collapses to 6/5 cotangent of half t. Question 13. Two inverse sines whose arguments are a sine-cosine pair in disguise. The second term is just the inverse cosine of x on this interval. For x between 0 and 1, inverse sine of root 1 minus x squared equals inverse cosine of x. So y is the constant pi over 2, and its derivative is 0. Question 14. A symmetric relation in x and y under square roots with a target derivative. Isolate, square, and factor. Y emerges as an explicit function of x. Move one term across and square both sides. Rearrange and factor the difference of squares plus the mixed term. X equals y only at the origin, so the second factor vanishes. Solve for y. Differentiate the explicit form with the quotient rule. Exactly the required result. Question 15. A circle of radius c and a famous expression that must not depend on the center. Differentiate implicitly twice, then substitute into the big quotient. First implicit differentiation gives the slope in terms of the offsets. So 1 plus the slope squared is c squared over y minus b squared, using the circle equation. Differentiate the slope again with the quotient rule and substitute the same identity. Assemble the quotient. The offsets cancel completely, leaving minus c, a constant free of r and b. Question 16. An implicit relation mixing y and the shifted angle a plus y. The sign subtraction formula will close the proof. Differentiate implicitly, remembering the product on the right. Collect the derivative terms and substitute x from the original relation. The bracket becomes the sign subtraction formula divided by cosine of a plus y. Sine over cosine a plus y. Divide through the required derivative. Question 17. The involute pair from exercise 5.6 returns, now asking for the second derivative. Differentiate the parametric slope with respect to t, then divide by dx by dt once more. From the earlier computation, both parameter derivatives simplify, and the slope is tangent t. The second derivative is the t derivative of tangent, divided by dx by dt. Question 18. The cube of the modulus, smooth enough for two derivatives, even at the corner point 0. Split into the two sides of 0, and check the meeting point. For positive x, the function is x cubed. For negative x, it is minus x cubed. Differentiate each side twice. At 0, both one-sided second derivatives tend to 0, and the first derivative 3x squared and minus 3x squared also agree at 0. So f double prime exists everywhere. Question 19. Differentiating one identity should manufacture another. Treat a as the variable and b as a constant. Let a vary as x with b held constant, and differentiate both sides with respect to x. The left side gives cosine of x plus b. The right differentiates term by term. That is the cosine sum formula. Question 20. A pure thinking question, continuity everywhere, differentiability failing at exactly two places. Corners are the standard way to break differentiability without breaking continuity. Yes, take the sum of two shifted modulus functions. Each modulus is continuous, so the sum is continuous everywhere. At 1 and at 2, the graph has corners. The one-sided derivatives differ by 2 at each, exactly as for a single modulus. Everywhere else, f is locally a straight line. Question 21. A determinant whose top row carries functions and whose lower rows are constant. Expanding along the first row exposes constant cofactors. Expand along the top row. The three cofactors involve only the constants L, M, N, A, B, C. Differentiate, the constant cofactors pass through untouched. Reassembling that as a determinant puts the primed functions in the top row. Exactly the claim. Question 22, the final one of Chapter 5. An exponential of inverse cosine with a second-order identity to verify. Take logs, clear the root, and differentiate a second time. Logs give an inverse cosine x. Differentiating produces the root in the denominator. Multiply up to clear the root. Differentiate this product. The root's derivative brings minus x over the root. Multiply through by the root and use the boxed relation to replace the right side by a squared y. Rearranged, that is the required equation. That completes the miscellaneous exercise, and with it all of Chapter 5, Continuity and Differentiability. In the next video, we begin Chapter 6, Applications of Derivatives with Exercise 6.1. Thank you for watching. If you found this video helpful, do like it, subscribe to math tutorials, and share it with your friends.